So you're going to have, and remember also from the last time we met, you're going to have multiple origins of replication with multiple polymerase molecules all performing replication, but DNA replication all at the same time. And they're eventually all going to meet. So we're not just having a single enzyme on each strand do this, we have multiple enzymes doing this all at the same time. And I'll be able to show you this here in just a second.
You mentioned the GC sticking together.
Uh-huh.
I understand that the GC content gives some indication of how likely the strands are to stick together. Are they more prone than the ATs?
Not so much that, but if you think about it, which would be harder to pull apart if I were trying to separate two strands of DNA? One that's predominantly A and T, or one that's predominantly G and C and Y? G and C, Y. 3 hydrogen bonds. Okay. So typically what happens, Richard, is that with G's and C's, there's just that much more energy in the bonds because you've got that extra hydrogen bond. So it makes sequences that are GC rich really, really, really hard to pull apart. Which is why if you're ever doing any work in like cloning or anything that requires primers or oligos, you always look for AT rich sequences compared to GC. Because when you go to melt the helix apart, it's going to be easier to melt it. It's going to have a lower melting point if it's just A's and T's instead of G's and C's. Okay. All right, so just so you can see what this looks like in a replication fork and a bubble. Okay, so here's our origin of replication. The red represents areas where we have placed primers using primates. The blue represents the actual DNA that has now been synthesized by DNA polymerase. And there's a couple of things I want to bring to your attention. First and foremost, at a replication fork. So there are 2 replication forks shown up here at this replication bubble. At a replication fork, whichever strand that is being synthesized by the polymerase is the strand that is moving into the fork is referred to as the leading strand of DNA. So notice, at each fork, we have a different leading strand of DNA. Absolutely. Okay, so at a replication fork, whichever strand of DNA that is being synthesized by DNA polymerase is moving into, or being synthesized into, the replication fork is considered the leading strand. That right there is the leading strand. Okay? The one that's going to be made into those fragments, where the polymerase does a little bit, then has to hop back and do a little bit more, and hop back and do a little bit more, that's going to be the lagging strand, which makes sense. The leading strand is going to be continuous, and is going to be able to just continue to produce or synthesize DNA. The lagging strand, however, is going to be limited because it's only going to be able to make a small piece depending upon how wide the replication fork is, and then it's going to have to jump back and do it all over again. And again, and again. Yes, Mary?
What happens when the leading strand, or what happens to the replicated DNA?
That's a great question. So, are you asking like for the leading or lagging? For the leading? So what happens to this DNA?
Yeah.
Well, the one thing they don't show here is what interactions are actually happening between this dark blue strand and this light blue strand of DNA. In other words, what's that? Well, during replication, so this polymerase is looking on this strand here, and it sees an A, so what is it going to put? A T. What are those A's and T's going to do?
Stick.
They're going to form hydrogen bonds, okay? Exactly. There are hydrogen bonds that are occurring between this top strand and this bottom strand there. And the same thing can be said for these fragments, which is why these fragments don't just float away. Because those fragments have A's, C's, T's, and G's that are going to form hydrogen bonds with their respective nucleotide partner. Yes, sir?
I have two questions with that.
Okay.
This slide makes it look like both sides of the strand eventually will have leading and lagging strands.
Yes, that is absolutely correct.
All right. And the other one is the same process used for RNA replication and DNA replication?
RNA replication, now when you say RNA replication, are you talking about transcription where we make an RNA transcript off of a DNA template?
Yes.
That is going to be different, and we are going to talk about that in the next chapter. It's going to require a different polymerase called RNA polymerase, but some of the principles are going to be very similar. Okay? One of the primary ones is the direction in which it's going to synthesize. Polymerases are always going to read the template strand from 3' to 5', and they're always going to make or synthesize their new strand of nucleotides, whether it's RNA or DNA, from 5' to 3'. Yes, Marita?
So on the top string, the prime is moving to the right?
Right here, and right here, and right here, and right here?
Yeah.
Okay, so this is a great point. Notice that the origin of replication actually kind of acts as an invisible line for us to divide this picture in two, because we've got two replication forks. So if you wanted to label this DNA, this double-stranded DNA molecule, the dark blue, this top strand here would have a 3' in there and a 5' in there. The bottom strand would have a 3' in here and a 5' in here. I would strongly recommend you label it. Like right now, if the picture isn't teeny tiny. I strongly would, because it's crucial that you label it that way so we can understand why we have a leading strand up until this point and now we have a lagging strand. Okay, so 3', 5', 3', 5'. Yes,
So
sir.
is it like where the black letter order of replication, is that like where that, the non-diagonal where that stops, where it shows like a split, and then?
No. This, here, are you talking about here?
Yeah, like
This-
where 5' is, would be the bottom.
Right, so this 5' here, on this drawing I have, would be that right there at the top. And this 3' here would be that. This 5'
Is the dot?
would go all the way over to here. Okay? Now, remember about the origin of replication. It marks where replication is going to begin. So originally, here's what this DNA strand looks like. Before we open it up, this is what it looked like. Okay? So, where those two dots are, is the same as what we see up there. Now, when we open this strand up just a little bit, so I'm going to open it up just a little bit. We've got a tiny bubble here, where we're initiating replication. Okay, here are my origins. Okay? Several things are going to happen. First and foremost, we're going to have at minimum, 4 polymerase molecules that bind when we open up this origin of replication initially. The first is going to bind here. And it's going to start to move from the 3' end, which technically is here for it, and it's going to go in this direction.
I just don't get, like, I understand that, I just don't get why it's open and then supposedly detaches, but then it's still continuing.
Why I've only drawn it like this? I've only drawn it like this to focus on one of the 2 replication forms.
Oh,
If I wanted to, I could draw it like this,
oh, okay.
and then wrap it around.
Okay, yeah, that just,
Okay.
I was like,
No, that is kind of confusing. So, okay, the next polymerase would attach there, and it would make a little piece of DNA, and then hop back as the fork opened up more and more. Okay, then a polymerase is also going to attach here, and similar to this one, it's going to make a little piece of DNA, and then it's going to have to hop back as this fork opens up more and more. And then one final polymerase is going to start making one continuous strand of DNA in that direction. So notice,
It's the same DNA polymerase on the lagging strand when it attaches and reaches the end and pops off, or is it replaced by another one?
most likely, you're going to have 4 all working individually. So when you first open up, so let's say we're first making this fragment, and the start of this strand and the start of that strand, 4 polymerases. One that binds to this primer, one that binds to this primer, one that binds to this primer, and one that binds to that primer.
Actually, no, there's multiple DNA polymerases doing the work of the lagging strand.
Right. That can be the case a lot of times, depending upon the state and how quickly you're trying to get it done. There can be multiple polymerases, because why wouldn't the cell utilize more if it could be more efficient? Yeah. Okay, so here's what's going on at any of these particular replication forms. Okay? So you've got helicase unwinding the helix, single-stranded binding proteins that are binding to the single strands, keeping the DNA from religating to itself or from attaching again through hydrogen bonding to itself. And then you've got this DNA polymerase 3 that attaches with this sliding clamp, and it recognizes the RNA primer that was laid down by primates as its starting point. Okay? This RNA primer, the initial one at least, is going to be placed right around the origin of replication. So, a couple of things about this, and I guess the first thing is there are multiple DNA polymerases. The DNA polymerase involved in making this long, continuous strand of DNA, or that's going to perform the majority of the elongation during replication, is DNA polymerase 3. Okay, there are going to be a couple of other DNA polymerases with altered functions that we'll talk about here. But DNA polymerase 3 is primarily the one we're talking about when we're talking about DNA replication. Now, showing you this picture, and this is one of the things I don't like about the book, it makes it appear as though, well, if I were to ask you, from this picture, does it look to you like the DNA polymerase is moving, or that the DNA itself is moving? What would you say?
The polymerase is moving.
The polymerase, right? Because they show it to you here, and then they show it to you down here. Okay? What actually happens in the cell is the polymerase, you can think of it instead of like a train on a track, think of it as though I had a piece of rope, and I'm the polymerase. Am I going to walk along like the rope like this? That doesn't really make much sense. Instead, what would be more likely if I wanted to get to the end of that rope? What would I do? I'd pull it, and that's what the polymerase is actually doing. Is it's pulling the DNA through it, and as it does, it's synthesizing the new strand of DNA.
Well, that would mean that a couple of things. One, does it use motor proteins for that?
There can be energy that is utilized to actually pull the DNA through or to move the DNA. Most likely, there are going to be secondary proteins that assist with moving the DNA through the polymerase.
Okay, well,
The polymerase itself is not going to move.
So
The-
the polymerase is
Stationary.
there while the DNA itself or the strand is
Right.
getting longer.
What-
What's actually happening is the DNA is being spooled through the polymerase. Yes, Richard?
what holds it stationary?
Stationary is a relative term. By stationary, I mean this protein is not actively moving down the strand of DNA.
Well-
It is staying in remotely the same place as the strand is pulled through it.
Even so, you would think that the DNA strand would be a lot larger, and just by pulling on the DNA strand, it would pull it along. And is it that much? Is it a lot more massive than the strand, or?
The polymerase itself?
Yes.
No. It's not more massive than it. It's just most likely more convenient to be able to just spool the DNA. Because the thing is, every time this protein would in theory have to move or exchange energy for it itself to move, you run the risk of it either becoming detached or something else happening. However, if it can actually just act as a spool, and instead all you have to do is pull or thread the DNA through it, it's probably going to be a little more easy to manage. I honestly don't know off the top of my head why it happens this way compared to the other.
I'm just thinking Newton might not approve of that.
Possibly not, but I guess Newton didn't really look so much at DNA polymerase. All right, a couple of things. First and foremost, let's talk about those fragments that are made on the lagging strand of DNA. Okay? When DNA polymerase has to work in the direction opposite or away from the replication fork, it's going to make these specialized fragments, which are the best and I think most fun words to say in all of biology. They're called Okazaki fragments. Okay?